For those that don't know who I am, my name is Steve Turrisi. I'm the Senior Director of Technical Services here at JL Audio. I am joined, as always, by my buddies, Kevin and Rob. Kevin's joining us from the greater Pittsburgh, Pennsylvania area. Please say hello, Kevin.
What's happening, everybody?
Excellent. And down in Southern California, where the fog has been epic lately, is Mr. Rob Haynes. Please say hello, Rob.
Hello, Rob.
Had to do it. So I am here at our main facility at JL Audio in Miramar, Florida. The building I'm in is right next to where we do the manufacturing and some of the other logistics stuff. I'm here with the technical support team and the marketing team, and I'm here today to talk to you a little bit about a recommended process and method for tuning systems. So this has been like for us, it's been our life for like 2.5, 3 years. Just focusing on this process. So I want to get into it. I'm going to go ahead and share my screen. You guys can do that for me. Let me pull this up here, boy. Like I said, I'm not accustomed to the whole presenter thing. There we go. So we have developed a bit of a step-by-step process, and this is something that we've been following for a long time. So I want to kind of touch on the agenda of what we're going to cover. We're going to talk about what is tuning. We want to define what that's all about. We want to talk about why you may need a process. A lot of people don't have a good process. And we also want to talk about what that process should include. I also want to talk about how you can save time during this process. There's certain areas that you may be able to save some time, some areas that you shouldn't save any time. You should spend the time. So we'll get into that. And I want to talk a little bit about why auto-tune typically, how do we say this, fails to meet expectations. So on the heels of that, we want to talk a little bit about what is a good automation, what good is automation, what does it do for us? And then finally, we'll get to that recommended process that we've been talking about. So getting right into it, we'll talk about what is tuning. So I do want to ask you, I know there's a bit of a delay on the Facebook chat and whatnot, but I want to ask, what do we think tuning is? Like, what is the tuning process? And, I remember when I was thinking about this presentation, some of the things that I had in mind what tuning was. And when I asked a couple of people, I got very different answers. So I want to see what the audience is thinking. What is tuning? What is that all about?
Well, so while we wait for the delay there, I have to admit, in the past couple of years, it's crazy to me how far tuning has changed from when I first got into the 12-volt industry in the early 2000s. It was set your levels on your amplifier, set your filter frequency, maybe a slope, and call it a day. And
done. Exactly.
It changed since then.
Yeah, and even then it was considered tricky, and there was some magic to it, right? There were EQs here and there. Some of them were really expensive, so a few people actually had them, right? So, but yeah, you're right, Rob, that this whole process has changed quite a bit. But I think ultimately, when we get to the answer of what is tuning, I think you'll see how what's old is new again. It's like, it's not really that different. There's just more controls, I think, anyway. So what kind of answers are we getting?
So we did get from Jeffrey Hald saying tuning is correcting all of the imperfections in the system to meet our target response. Sean Mullins said it's matching energy levels and time for multiple components to work together.
Ooh, I like these answers. Yeah, these are really good.
So good
answers.
When I asked a couple of our engineers, they gave very detailed and methodical answers, and I was like, "Hang on, let's go higher level on this." Instead of getting that deep, I think tuning is adjusting the system to ensure that it performs a certain way. Now, the distinction here is how it performs is really up to the user. So either the customer or the shop that's doing the tuning, whatever the case may be, it's their preference. So I guess the point is that the goals may vary. What you're looking for may be different than what your customer may be looking for. And as a case in point, let's talk about probably the more common thing that is thought of when it comes to tuning. And that's people that are looking for sonic performance, things like imaging and tonality. If they start saying things like to make sure it sounds good. To Jeffrey's point, tuning is correcting all the imperfections in the system to meet our target response. That's really good. And I like what he's putting there. Correcting the imperfections. The imperfection that Jeffrey's referring to is what we call the three pillars. It's frequency, level, and time. And Sean builds on that by actually saying the word time specifically. Those are the three things that we're after. So when it comes to a sonic performance for imaging, tonality, and sounds good, correcting all of those to line up the way they're supposed to can get us there. Now, I put there reliable because we don't want stuff to break. I am sure that you can extract more stuff out of an individual speaker in the system, but if it breaks, that's not exactly what we're looking for. So tuning in this case is the process of making it sound the way we want, like Jeffrey and Sean were talking about, as well as maintain reliability. Most people don't think of this, but when it comes to SPL systems, it's very similar. In this case, we may want it like really loud at, I don't know, 70 hertz. We want a single note wonder. And maybe we want it reliable. Maybe. Not always. Is some people that really don't care, they just break it anyway. But you can do the same things that Sean and Jeffrey were talking about, where we align the system, both frequency, level, and time, to make sure that we're getting that type of performance. So tuning, in my opinion, is adjusting the system to perform a certain way. And whatever that way is, we use whatever tools we can to get us to that goal. So that's what I think. But to get there, you got to know where you're going. You got to know what's going on, and you need a process. And a lot of people, when I ask them what their process is, I get things like, you said, kind of like what Rob was saying. I said high and low pass filters, and then maybe I do some EQ. Oh, yeah, and I've been using a tape measure for delay. That's not a process. Those are the things that you've been doing. You need something that defines exactly what order that goes in. If you want something consistent, you've got to lay out a step-by-step procedure. You need a consistent process if your goal is consistent results that perform well. So I like a process that provides direction, that tells me what my next step is. All right, I've done that. Now what? Now what? Now what? In any given day, we're all being pulled in a million different directions. And if you're trying to tune a system while being pulled in a million directions, your process is going to go all over the place. You'll simply start chasing whatever you think is next. Consistent process should give you consistent results. So let's follow that process and make sure that we're staying on track. And now every system needs to meet or exceed expectations. And what I mean by that is sort of the goals that we just talked about. The sound quality goal or the SPL goal. There's a certain level of expectation that needs to be met or exceeded to make sure that the shop or the customer is happy, or we're happy if it's our own system. There's a certain threshold. A process can help us meet that threshold consistently every single time. Now, when I hear the word process, very often I think of, oh my gosh, I got to follow this process that's going to take me a longer amount of time. So it begs the question of where can we save time? Now, the truth is we all want to get done with whatever we're trying to do as soon as we can, but no sooner. So we can't take any shortcuts. We need to get the job done, whatever that job is, in this case, system tuning. So if we want to save time, again, when I hear process, I think, oh my God, I have to, it's going to kill my time. I can't spend the time to go through the process. I got to get it done. Now, when it comes to saving time, a process that allows you to dial things that can be quantified faster and with a very defined goal, that means you know when to stop. That's where you can save time, is being aware of what you can measure that is quantifiable. So sounds good is not measurable and it's not quantifiable. There is no value associated with sounds good. You can't target that. That is where you can really spend a lot of time. If you can measure it, that means you can target it. And if you could target it, then you know when to stop. Once you have reached that target, you don't need to do anymore. You move on to the next thing, whatever that may be. So when it comes to saving time, the best thing to do is have a process that allows you to quantify and target something and get to that goal as quickly as possible. Knowing when to stop is vital. That's where you can really save the time. There's other parts that you can't skip. The part of the tuning process is listening. You cannot skip this step. And you cannot cheese out on any of the time aspects of this. You need to spend the time listening to the system. The objective analysis, the stuff that you can quantify and put a number on, that's really important. And that's something that you can know when you're done. When it comes to listening, the good thing about it is this is the best part. You're listening to audio, which is what we all want to do. The best thing about this is you spend the time, you listen to different tracks, you listen to things, and you determine if your objective analysis, everything that's quantifiable, has done the job that you want. You make some minor changes, and then you move on. Even a well-targeted system needs to be listened to confirm that it sounds good. The machines can only get you so close. Humans have to listen to it and determine if we hit it, which is going to lead me to what I think is why auto-tune systems tend to fail. I mean, everybody wants this. We all want it. But if we're honest about it, how many of them actually deliver on the promise of a great sounding system every time you hit that little button, right? The way I see it, it fails to meet expectations reliably because a lot of the routines seem to imply that us as a user, we don't understand what's happening or even why it's being done. So just hit this button and we'll take care of the rest. You don't need to worry about it. That bothers me. We have very limited, if any, control over the goal or the outcome. So that means whatever the company that created the auto-tune has created, that's what you get. You can't change that, and you don't even know what that is. It just says, you're done. let's go to the next thing, which is, you're done, right? A lot of the stuff is also done in the dark, which means you have no idea what they were actually looking at or what they were trying to adjust. Very rarely do we have control over any of the operations that are being done. We don't know what they are, and we have no control over them. So when I say invisible work, what I mean by that is something's happening that you don't know exactly what that process is. You're blind to it. It's invisible to you, which leads to the next one, which is what I call the man behind the curtain. We very rarely see what was actually done. So we don't know what they're doing, and we don't know the result of it. Unless you're really careful about taking before and after measurements of all the different aspects of audio, you have no idea what that auto-tune has actually done for you. So we're not in control. And I think that's why auto-tune fails, because like I said before, we have to listen to this stuff. Humans have to listen to it, not a computer, not a microphone. We have to determine if it succeeded or failed. And we have no idea what was changed. We have no idea how to make it even better, or even what the goals were in the first place. I think auto-tune fails because we're not in control. The desire for auto-tune, one of the big ones, is obvious. It's faster. Instead of adjusting everything on your own, you hit a button, it does it for you. Who doesn't want something like that? So to me, that speaks to what good automation really is. Like, what is proper automation? What will save us time? Well, when I think of the word automation, I'm a computer geek, and I spend lots of time trying to make my computer do work automatically for me. And what I'm not actually saving any time, because I'm programming all these automations, and that's taking time. But ultimately, at the end of it, there's something that I am looking for. I'm human. And to me, a good automation is going to remove me from that equation. It's going to be consistent in the process. It will be infallible. How often do I forget to do something? Very often. Making an automation allows you to have a process that's defined and repeatable every single time. It does step A, then B, then C, and it doesn't skip one. It knows better than to skip one. It doesn't forget the steps, and it's methodical. That is key for automation. And it also makes no assumptions. I mean, I can't tell you how many times, you're doing a system. I know I wired the tweeters right. I don't have to check polarity. Don't make that assumption. That's something you do want to check. You want to make sure of that every single time. I'm in a rush. I don't need to check the high pass filters. I know I set them right. Don't make that assumption. That's where your process falls down. Automation doesn't make assumptions. It doesn't skip steps. It's methodical and infallible. It does the same thing every single time. That's a good automation. But the thing that a lot of people think of with automation is that it's fast. And it is fast. Computers can typically click a lot faster than you can. So if you're constantly doing the same clicking over and over and over again, having an automation that can click faster than you can save you time. So what is a good automation? What makes for a good automation? Well, this is my opinion. A good automation is something that's visible, something that shows you exactly what's being done. So when it goes through this process, you can see what's being done and see what changes are being made. It's also fully what I call overridable. That means that you can accept or change or completely get rid of whatever actions were done. You don't have to accept what was done. In other words, nothing is etched in stone. This is all in your control. So good automation is visible and fully overridable. You have complete visibility and complete control over what's being done with the automation. It just does it in a process and faster than maybe we could do on our own. That's what I call a good automation. It's not automatic per se, but it is automation working for you, my opinion. Okay.
At the bare minimum, like get you in the ballpark to fine tune it, not do everything to get to the fine tuning.
Exactly. Point. And Rob, that's an excellent point, because what we're talking about here is the objective analysis, meaning something that's not subject to, I think it sounds good or I think it sounds bad. It's a number. It's a value-driven thing. So when we look at, we're going to talk about matching to target for your equalization on your frequency response, you can actually see values associated with that. And when the values match, they match, period. There's no, I think they don't match. They either match or they don't match, as opposed to, I think the imaging sounds great. And Rob would say, I think the imaging sounds horrible. Those are subjective analysis. And that's why the listening part's so important, because if the objective is perfect and the person doesn't like it, the objective has to change. You have to shift that to make it sound the way the user, the listener, actually wants. Good automation gets you, like Rob just said, to the part of listening faster and better than just doing it by yourself manually in most cases. So finally, I'm going to get to the process, which is, I think, what most people really care about here. Now, I kind of debated putting this slide in. It sounds kind of bold, but I want to make something clear. I'm sure that many of you have tuned systems before, and you most likely have done a really good job. But by the fact that you're sitting here right now watching this presentation, it's implying that you're open and interested in maybe doing it better. But better, that implies that it has to be different, because if you keep doing the same thing over and over again and you're expecting better results, that's the definition of insanity. But if you want to be better, you have to try something different. Now, different doesn't mean better, but better has to be different than what we're currently doing. So by watching today, we appreciate that, and we're going to share with you a method that we think may be better. Try it. It may be different. It may be the same as what you're doing. I don't know. But let me go through the process. And I want to give like kind of a big overview of what we're going to talk about. In general, we let the data be the guide. We look at the analysis of a signal of what's going on in the system. We let the data present itself to us, and we look at that data and we make changes based on what the data is. We try to forget any of our preconceived notions of way it's supposed to be or what's supposed to happen or what I've always done. Let the data tell you what's going to be correct or incorrect for the objective analysis. And what I mean by that is there's a bunch of terms and things that I'm putting on the screen right now for you that we tend to look at. Some of them may be familiar. One of them in particular, like a EQ to target. The other ones, you may do something like that, but it may not be exactly that. So what I'm going to do now is I'm going to break down this general overview into a general process of how do we actually go about doing this. So let's dig in a little bit deeper. The process in general looks like this. The first 4 steps is what I call pre-flight, and that involves system design and system installation. And a lot of you are thinking, whoa, that's not tuning. Yeah, it is. Because if you don't do a good system design, if you sell, or install the wrong equipment, or you install it wrong, the best tuner in the world is never going to get the most out of that system. They may be able to, they may get the most out of that system, but that system may not be as good as it could be. So the tuning process starts with choosing the right equipment for the goals that you have in mind and installing it properly so you get the most out of that equipment. Don't skip those steps. Pay attention to the gear that you're buying.
Aligning your phase for the mid-bass drivers into the subwoofer will have no help on the mid-bass if you have a driver just thrown in a hole that's not properly sealed without deadening material and openings everywhere. So it's got to be done the right way.
100%. Absolutely, Rob. Excellent point.
What's funny
go ahead.
Is I look at this and I see micro processes that happen during this initial stage here too, right? When you're designing your system and you're mentally planning all of that stuff out, that is a process within a process. And then your installation, you're going to go through a process of doing your installation.
Yeah, you're right.
Yep. And then you get to your tuning process. And so it's a good thing. Have a plan, execute your plan, and walk through the steps, and you'll end up with good results.
This is very true. Excellent points. So step 3 is checking your configuration, make sure things are correct. That's both the physical world as well as the digital world. So make sure your wiring in the vehicle is correct, especially if you didn't do the install. I can't tell you how many times I've sat down to tune a system, and I spent 2 or 3 hours trying to figure out why that left tweeter is not playing the left tweeter. So you have to check all of that before you get too far into it. And then so then you have to go in and make sure that each one is labeled properly. So when you're in the software, you know that when it says left tweeter, you're actually working with a left tweeter and it's wired correctly. All of these things are what I call pre-flight. And I don't care what system you're tuning, we should do this on every single system. This is, to me, it's non-negotiable. All right. Next up, step 5 and 6, we're going to look at polarity, and we're going to set our initial delays. Focus here on that word initial. So the polarity, a lot of people are using a polarity checker to check polarity. We'll get back to that in a little bit. And a lot of people using a tape measure to set their initial delays. The word initial is important. You have to start somewhere. And by setting those initial delays, you at least get the system aligned to a certain point. The tape measure method, you basically put a tape measure from like the tip of the driver's nose, right? From that point to each one of the drivers in the system, you do some basic math, or maybe your software does this for you. You put the values in there, and it'll put in delays so that the signals will all arrive at that point at the same time based on the measurements you take on the tape measure. If you understand that these are initial delays, you're in a good spot. If you think that they're the final delays, you may be disappointed later when we get to the part where we look at how the drivers actually interact. So we'll come back to that. Steps 5 and 6. Steps 7 through 9 and step 10, this is somewhat of an iterative process. And what I mean by that is you may do them out of order. You can actually change things up as you go. And that's where letting the data be the guide becomes really important. So when it comes to defining the targets and then applying high and low pass filters to drivers, if you're looking at the data compared to your target, and the data implies that you can shift the target to better match the data, that's something that you might want to consider. So then you go ahead and you redefine the targets based on the data, and then you go forward and then you apply your filters and then you EQ to the target. You let the data guide you to see if your targets were right in the first place, and then you move forward from there. And so steps 11, that is optimizing driver interactions. And what I mean by that is, just for simplicity, we'll talk about a left mid-bass driver and a right mid-bass driver. You want to make sure that when those are playing, that they're playing together in time. So notice that it comes after the matching to target. That's frequency and level domain that we're talking about there. This is more of the time domain. Remember the 3 pillars. The time domain here is to make sure that the 2 mid-bass drivers are going to play as if they're playing together in time. They already match in frequency, and they're already properly set in level at this point in the process. That's what I mean by driver interactions. I also mean a complementary driver. So the subwoofer to the mid-bass, we want to make sure that they are playing together in time. If they're not playing together in time, the summation, when you combine them together, you will get less output, you get less performance. So the driver optimization, we're manipulating time-based things to make sure that everything's playing together in time. That's step 11. Step 12 is the most important step, and it's the most fun step. It's listen. You get to listen to the system. At this point, it's no more objective analysis. It's no more looking at numbers and seeing what lines up. This is when you're sitting in the vehicle with the computer next to you so you can make some minor adjustments to make sure it sounds the way you want. This is the fun part. Spend as much time here as you possibly can. It will reap benefits every single time, I promise you. And the one step that I'm going to tell you to do it, and I'm going to tell you I forget to do this every single time, and it's embarrassing. And I'm willing to bet if you ask almost anyone that's on this session right now, they forget to do this as well. And that's to recapture the data. If you go through the process of listening to the system, you should document the final results because you've probably made some changes. Maybe you adjusted a tweeter level, made an EQ cut at a certain frequency that was a little bit bothersome to your hearing. If you find that you're constantly making the same changes, system after system after system, you can use step 13 to quantify that and go back and change your target. Save you more time later on. If you're always doing, I don't know, maybe you're making a cut right around 2K of a couple of dB every single time, maybe you do that on your target. So when you do your match to target, you've already put that cut in and saves that time later so you can listen to other aspects of the audio.
You know,
the truth is, go ahead.
I was going to say, if we remember to do step 13, we could, handle Sacktown Steve's request of showing what a auto set, an automated or with all the micro automations, what the tuning looks like compared to after the listening and salt and pepper. But, if we're not good at remembering step 13, but maybe we need to start being better. So
we need to get better at it.
The final.
I know I need to get better at it. That's for sure.
And the nice thing is for Sacktown Steve there is if you capture that, like Steve kind of mentioned, you just adjust your target there and then you start getting even closer. So it's not so much of what that micro automation is doing. That micro automation is getting you to that target and getting you very, very, very close to that target. By adjusting your target, it's going to make that bigger difference at the end than going from maybe using the micro automation to doing it manually, going through there and changing that. So change your target. If you find yourself making some cuts and salt and pepper on there that are the same, change your target.
Consider it anyway. So what's funny about this, Kevin, and so I'm glad you bring that up. We've heard from people over the past couple of years about what's your target curve? What's your target curve? They're looking for a target curve. Step 13 is you're defining your target curve. So you listen to a car, you capture that response. You listen to another car, you capture that response. And as you capture all those responses, if you listen to car A, for example, you say, wow, this sounds really, really good. You capture that response and you see that target shape, right? Then you listen to another car. This one sounds horrible. You capture that response and you compare the two to see where they differentiate. That's how you start developing your own target curve. So the one that we recommend is just the one that we've had good success with. It seems to get us closer to where we want faster. But there's lots of different target curves because other people have had different experiences, and those curves help them get closer to where they're trying to get faster. That's what a target curve is intended for. But I will add, a bad target curve with the best process means every single time it'll be bad. So you need to make sure, like Kevin was saying, that you capture that good information and define a good target.
I think Jeffrey suffers the same problem we do with step 13. He's just so darn excited to listen 100%. To it. He doesn't want to put the mics back in.
I know exactly what he means. I totally do. And, to be honest with you, if you're working in a shop, you go through the objective analysis, which is what we're going to go through in just a moment. We go through the objective analysis. We put the butt in the seat with the computer there. We make our adjustments season to taste. At that point, we're so elated that this system sounds really, really good. We get the customer involved, and you're not going to put the mics back in then. You're just going to let the customer leave or whatever the case may be. Or in the case of Jeffrey, it's his own car. He's just so excited that it sounds so good. He just wants to stay there and keep listening. Totally get it. Totally understand. But try. I know I keep forgetting. I know Nick keeps forgetting, but try.
Okay. It's time to go for a ride.
Exactly, right? All right, so that's the general process. And I do want to share with you, and I kind of color-coded the sections just because there are 6 different sections. There's the pre-flight, that the first measurements, then the iterations step of matching the targets and setting your levels, optimizing the drivers, listening, and then capturing the final results. Those are the 6 sections. When you're using Tune and Max, the process is really the same. The same breakdown. You have the pre-flight stuff is the same. Steps 5 and 6 are actually compressed into a single step, and I'll show you how we do that in just a few moments. Steps 7, 8, 9, and 10 are not only iterative, they're technically as one step. And the way we go through the process, this is where we save time by being able to compress all of this. We're not skipping anything. The process is the same. It's just the tools that we're using allow us to be very efficient at doing them. Next up is optimizing channel interactions, right? And then, of course, the listen, and the recapturing of the data at the end, which we'll all forget. Okay, so let's go into each one of those steps. I kind of jumped ahead a little bit on this. System design, you got to buy or sell the right stuff. Rob kind of pointed out some interesting things regarding installation. I'll go a little bit further. We've had customers that call us up that their system's not performing well, and we start drilling into it. They were sold a pair of like 3.5 coaxials and a 12W7. There's no way I can tune that system to sound good. It's just the wrong equipment. It may be good equipment, but it's the wrong system design. They chose the wrong equipment for that particular application. And then if you follow what Rob said earlier and you do a really crappy job of installing that, there's no way a system tuner can ever extract enough performance out of that system to make it work the way it really should. So you got to do those 2 things correctly. The initial configuration and signal routing, you got to make sure your physical and digital routing is done correctly. And then from there, you got to make sure it's been done correctly and labeled correctly. So your identification of channels is correct. Is left really left? Is that really a tweeter? Listen to it if you have to. Just say, yeah, that sounds like a high frequency driver coming from the left. Okay, that's my left tweeter. So just do that step. Again, I can't stress enough how many times I've gotten into cars and we've had to go back to these 2 steps at the initial configuration and checking the wiring, as well as checking the channel and speaker identification. Do this step. It doesn't take all that long. Next up is steps 5 and 6, which are our first measurements. There is an implied step here. If you're taking measurements, that's step 4.5. You got to put the mics in the vehicle. And the way we recommend doing this is we have a microphone array, something that looks a little bit like this guy here. So a microphone array, the idea is to put the microphone or microphones, in our case, in the listening position so that the listener's head is going to be approximated by the spacing of the microphones. We're trying to create an area for the measurements that make sense for the listener. The timing reference that we'll use for all of our phase measurements should be in the center of that. So if you're looking at a 5 microarray like the one we offer with Max, the center one is the red one, and that should be roughly where the driver's nose would be, or the center of their head if you could physically do that. And the other microphones can be positioned around that head. So as they're moving and shaking their head around, bouncing to the music or driving the car or whatever the case may be, that sphere that's being analyzed around that driver's head is what we're focused on. So you position that. We would recommend at that point, now that we have data that can be captured, that you stop right there and capture the noise floor of the system. When you're doing objective analysis, you need to be able to differentiate between what's noise and what the actual system is doing. So with the system not playing, you capture the noise that's being sent to the microphones at that position, and you save that as a trace that you can recall or hide or whatever you want to do, but you have that as a baseline reference. At that point, we think you should stop and think about what you're doing now, because everything up to now, we've done nothing to change the sound of this system. We've just configured it so that we can now take measurements and make changes accordingly. So if you're retuning a car that's already been delivered, or if it's your car and you like the way it sounds, you're just trying to get more, capture all of the details. How loud is it broadband, the whole system playing? How loud is each driver? Get that level. Check the high and low pass filter frequencies. Consider saving it as a separate preset so you have something to fall back on. Because very often when we go through the tuning process, a lot of it is about controlling energy. And if you take too much energy out of the system, you or your customer would be very disappointed if they brought it in and it was really loud, just didn't sound all that good. And now it sounds really good, but it's just not that loud. That level of disappointment we can't afford for us or for our customers. So we need to make sure that we have that baseline reference. The next step that we're going to do is basically reset everything. And that's when the changes will come in. Now, of course, the goal is to get it to be better and as loud or even louder if we can, but we need to be able to have a baseline reference. So now we get to step 5 and 6. Step 5 and 6 is when we confirm or reset all your settings. I would recommend resetting them. However, I would recommend keeping what I call a safety high-pass filter on your tweeters. As an example, so you have a tweeter in the car, a common crossover point or high-pass filter frequency would be, let's say, 5,000 hertz. So 5,000 hertz, a lot of the higher quality drivers that you're likely to be using when tuning your system can probably be crossed over lower than that, and probably should be in some of those cases. Just make sure it's safe. For the tuning process, we want to try to eliminate filters while we go through the first few steps of this process. Tweeters can be sensitive to lower frequencies if you play them too hard, too aggressive, or if you forget something. So I would recommend, instead of turning off the high-pass filter, set it to a lower frequency, 1,000, 1,500 hertz. This is not your final frequency. It's just to prevent the really low frequency stuff from going to the driver while you do those first layers of analysis. I am quite confident that the levels that you should be doing this at, which is not very loud, even 1,500 or 1,000 hertz on any quality tweeter for a short period of time is going to be just fine. I'm sure of it.
Yeah, to add to that, Steve, a lot of times I'll bring the level down of the tweeter in tune on my output section. On my output or my output levels, I'll bring that down, and then I will slowly raise that up to get to my target. That way I'm not bringing the tweeter on at a louder volume than I probably should too. And if you're tuning outside the car and you have your microphones inside the car, understand what level you are at going and playing inside that vehicle at that point in time too, because you don't want that tweeter railing loud.
It's real easy to forget that, Kevin. I'm so glad you brought that up, because someone around this building here blew a tweeter accidentally because he forgot that part. So yeah, that can happen. You need to be aware that this is a real system that's playing real audio through real drivers, and if you're not careful, like Kevin just explained, you'll be buying a lot of extra parts. Okay, so where are we at? All right, so we set our safety high-pass filter on the tweeters, and now we're going to check polarity, and you can do that with a polarity checker. And we're going to set our initial delays, and you can do that with a tape measure. Now, there is a distinction here. This is the general process. When we get to a specific process, like using Tune and Max, as I'll share in a moment, some of this will be done a little bit differently. And let's get into that now. When you're dealing with Tune and Max, polarity and impulse response measurements will be done at the same time. And the impulse response measurements is how we're going to set our initial delays. What an impulse response basically is it shows the arrival of audio at the microphone. So that's a time-based measurement. So you need some kind of reference for the time to actually make sense. So we're going to look at impulse responses so you can get a better idea of what we're talking about with arrival times and things like that. You can check polarity at the same time by looking at the direction of the impulse response. we're going to recommend that you start with the top tweeter or the top channel, which is channel A. And if you follow our recommendation, that would be the left tweeter. And then the next channel down would be channel B, which is the right tweeter, then the left mid-range and the right mid-range. And if you follow that process down, which is our recommendation, the process that I'm about to share with you can actually be done incredibly fast. It'll take me significantly longer to tell you how to do this than it will to actually do it. Okay, so you can use a tape measure if you're not using TüNing Max, but in TüNing Max, we can streamline this and be, I think, a lot better and faster at it. So let's get into it. What you're looking at here, this blue trace, as we call it, is an impulse response. And by looking at this, I could tell some pretty good things about it with some degree of accuracy. I could tell that this is probably a high frequency driver. And the way I could tell that is you see that it looks like a spike that's pointing straight up. The width at the bottom of that spike is actually pretty narrow. Lower frequency drivers would have a wider peak. In fact, very low frequency drivers, it's almost like there is no peak. It's like a mountain. I'll show you one of those in a little bit. So when it's narrow like this on this scale, when it's narrow, we can get a good idea that this is probably a high frequency driver. I can also tell that this is probably an electrical response because that spike goes up and comes back down, and it doesn't do a whole lot of what's known as ringing or noise on the right-hand side. So the way this is working, as the signal comes in from the left side of the graph, it goes through and it exits on the right. So stuff on the right is happening later. Stuff on the left is happening earlier. So I can see that there's a peak here, but we don't really care about the peak. The peak of this energy, because of the width of that spike, that peak may be way off from what we really care about. What we really care about is the start of that impulse response. So you'll see as you go from left to the right, there's no signal, no signal. So there's a little bit of wiggle. I'll explain that in a little bit. So you got a little bit of wiggle, a little bit of wiggle. All of a sudden it jumps up. This spike goes straight up. When it goes up, that's telling me my polarity is in the positive direction. If that was pointing down, that would be opposite polarity. Now polarity, if they're all opposite or all, if they're all negative or all positive, that's what we care about. We just don't want them different. We don't want some positive and some negative. We may end up that way, but this is all our initial settings. Our initial polarity and our initial delays will be set by looking at these impulse response measurements. Okay, so that's the shape and some of the things you can tell from this particular impulse response. But I want you to look here. This is what's known as a reference delay. That reference delay is going to become our new time zero. We're going to set a reference at the beginning of an impulse response as our reference. This is where everything is beginning, is kind of what we're saying. So when we take that and we look down on this part of the graph, that number there is now our new time zero. That's the beginning of everything. Now, I'll pause for a second here. This is a tweeter. And if it's our left tweeter, in this case, it's not, but this is just a really good example. If it's our left tweeter, it's almost certainly not going to be our reference delay. That's probably going to be something else later down the signal path. But if you set your reference delay and go to the next channel, and that one is showing up later, then you set that as your reference delay. We'll go back and fix everything again in just a moment. Just want to show you what we're doing here is we're setting a reference delay to set our new zero, and things that are happening to the left and to the right of it are either arriving early or they're arriving late. So when we talk about things arriving early, how can we fix that? We can apply delay. We can delay things that arrive early. If they're arriving late, the only way we can change that is to shift our reference to that new late arrival. You can't speed up time. So that's why we want to get a reference delay so that we know what's arriving early and what's arriving late. All right, so I have an extra build in there. In this one here, this is actually, again, let's kind of break this down. If we look at this red tweeter, we know it's a tweeter because it's a very narrow spike, is arriving late compared to what the zero is. It's arriving somewhere over like the +5 or 5 milliseconds late. That's late. So that one would have to shift our reference. We need to set our reference to wherever the beginning of that IR is. Now, if you look carefully at this, you'll see what's going on in this area here. Those extra wiggles, that's what's known as pre-ringing. Pre-ringing, there's several ways that you can wind up with pre-ringing, and it's way outside the scope of what we're trying to cover today. But I want you to see that even with the pre-ringing, we can still see the beginning of the impulse response and get a pretty good idea for our initial delays of where to set our reference or ultimately our true delay value if we need to delay this channel. So even with some pre-ringing, it's still okay. You'll also notice arriving later after the initial spikes there, you'll see it's kind of hashy. It's kind of, I don't want to say it's messy, but that's how you know this is an acoustic response and not electrical. In most cases, you'll see something like this where there's a bunch of extra stuff that's happening after the initial impulse of the signal. So after that, it's less important to us as much as we care about that initial rise, that initial change from the zero line, whether it's up or down. That's what we're looking for. Up is positive polarity, down is negative polarity. Okay, I'm going to challenge you guys. Here comes question time, so get ready. When we look at this, we have not changed our scale. I want to see, there's no help here. I want to see who could tell me what this might be based on what I've shared so far. So the scale is the same, right? So before we looked at a tweeter, which is a really narrow spike that goes up. You'll notice this one doesn't appear to be as narrow. It's also not as tall. So what I'm going to do now is I'm going to change the scale. I'm going to change the y-axis, the height of the impulse. And by doing that, you can now see it a little bit clearer. There's not as much pre-ringing. Any idea what we're looking at here?
It's in polarity.
It is correct polarity. You got that right.
Wait, I remember what anybody says here on the.
While we're waiting for some answers, I think seeing an impulse response like this is really cool because we've always talked about using the tape measure method, but this is a true representation of when the signal is leaving the speaker and hitting the microphone. And the reason why you have to have Max for this is Max has a built-in loop back. So when Max sends the pink noise out of Max, it loops right back in. So it's comparing from when it received the signal it sent out to when the microphone receives it. And having that gives us a lot more detailed and accurate representation of arrival time instead of, kind of guesstimating with a tape measure, because you've got grills probably. How do you measure subwoofers when they're facing the trunk? Do you measure where they bounce off of in the back? Do you measure to the front of the subwoofer? Do you measure to the back of the box? So this is really the right way to properly get your stuff dialed in. We didn't really talk about it because we didn't have a real efficient, accurate way to handle these types of measurements. But with Max and Tune 4, I mean, it definitely expedites the process with polarity and getting more accurate initial delays, which just makes it even easier down the line when you start looking at the phase and all of that.
Correct. And without doing this step, looking at phase is meaningless. We'll cover that in a moment. There's the famous saying that time is relative. So what Rob was referring to with the loopback has delay as well, but it's the same delay as everything else. So since all of it is relative to the same point, whatever that delay is pretty much offset, because now we're looking at the rise of the actual acoustic impulse response. So whatever that value is, I don't want to say it's not that important. You got to make sure that it's not, broken. But once you have that established as a reference and you create your new zero, all the other measurements relative to that new zero can be compared with a high degree of accuracy. The tape measure can get you close as well. This can get you closer, and I would contend that it can get you there faster. So that's the goal. So yeah, I am looking, and
we do have some answers. We do have some answers that came in. No, it's not cardiac arrest or an EKG. Jeffrey says he thinks it's a mid-range. It's not round enough for a mid-bass or sub.
So, Jeffrey, you've been paying attention, that's for sure. So, yes, this is a mid-range driver. It's a real speaker. You can tell by the energy that's happening after or later to the right of the actual initial spike. And what Jeffrey's referring to is not round enough. That sharp spike of the impulse response implies a higher frequency component to it that would not normally be present in like a mid-bass driver in most cases, and certainly not a subwoofer, as I'll show you in just a moment. So yes, this is an actual mid-range driver. Acoustic response, and it is arriving at roughly 4.7 milliseconds after the time zero as it's currently set. So there is no reference on this. Go ahead.
I kind of, just to add to what we were saying with the accuracy and stuff, and this is kind of how I look at it. The tape measure works really good and it gets you close, but sometimes you need to break out the calipers and really get your stuff dialed in. And this is like breaking out the calipers. You're going to get a really fine, detailed measurement that is going to be a little bit more useful and help save some time when you get down the line there. And that's
it's important to remember that this is the initial setting.
Yeah,
it's very likely that we'll have to go back and make some changes when we do the analysis of phase. But without doing this step first, phase is meaningless. We'll show you that. I also see that we did not obscure that this is a left mid-range output.
Eagle eyes.
Me and my labeling.
All right, well, then this will be easier than I thought it would be. What are we looking at here? The question I put on there, where is the IR? It's there. Believe it or not, there is an impulse response on this screen right now. But if you look over on the left side, the scale is such that you can't see any of it. So we need to change the scale to be able to zoom in and change the scale of the graph so that we can actually see what this is. And as you can tell, the bottom right-hand corner tells us this is a subwoofer output. So we're going to take this scaling and we're going to change it now. So this is what happens when we zoom in. Not only did we change the x-axis in terms of time, but we also changed the y-axis over here. You see that it's a lot tighter and more zoomed in. Now, when you look at this waviness, that's kind of what Jeffrey was talking about. It's very rounded. It's very long and very prolonged out there. And if you look at this point here, we don't use this peak. This is the high point. It's not the first point, mind you. It's not the first peak, but it is the highest peak. And that peak, if you look carefully, it's going to be hard to see on a small screen there. That's at plus 15 milliseconds. If you were using the peak to set your initial delays, you would be way, way, way wrong on this, which is why I think a lot of people don't use impulse responses, because I think they're looking at the wrong part of it. Could be wrong, but if you use 15 milliseconds in this case, it would be very different than using what we would use, which would be the start of the IR. And in this case, we've already set that as our reference delay. So if you look carefully, that's at 8.13 milliseconds is our reference delay. The value is not that important. It's just the reference point. From now on, we can use that as a reference point. I think we actually shifted it later, but that's irrelevant for right now. But the reference point is just that. It's just a reference point. We're going to shift things later when we start looking at the actual interactions. So I've been saying, and Kevin and Rob have been helping me out on this, that the polarity is obvious as well. If you'll notice this one, it's starting in a downward direction. That means the polarity is reversed. And what we can do is we can flip the polarity and change that response. Now you'll see it's identical. It's like a mirror image, but instead of going down, now it's going up. By looking at the impulse response, we can see the beginning of the impulse response and find out what our reference delay should be. We can tell if a signal is arriving before or after our reference delay. So we can either shift our reference delay or add delay to make them all line up. And we can tell the polarity of the signal at the same time and address it immediately in the DSP right away on the same screen. That's pretty powerful and very, very fast.
Nice use of captured traces as well.
Very good use of that. And we don't have to obscure it anymore. So that's kind of nice. So I have a couple of other examples to help you see what's going on with impulse responses. And this one here, if you look at the beginning of it, it's noisy. So this is, I believe it's a mid-range driver. Yeah, looking at my screen there, it's a left mid-range output. But look what's going on at the beginning there. It looks very different than it did before. What's happening here is there must have been noise when we captured this trace. Kevin, any idea what happened here?
Yeah, if you guys haven't known from the past 100 ones of these that we've done, I live next to a racetrack. It's not really a racetrack, it's a road. But somebody in their car drove down very loudly with their exhaust, and I was able to capture that trace while they were doing it.
And what I love about it is that, and that's, I wanted to show this in the next slide that shows a noisy capture, because again, if you don't have a good capture, it could be difficult if you don't know what you're looking at. But I'm willing to bet everyone watching right now sees that noise and still can see the beginning of the impulse response before that rise starts a little bit later. In this case, it's at 7.17 milliseconds. Again, that's irrelevant. You can see through the noise. Automations may not see through that noise. So having visibility to it is really important, and understanding what you're looking at is really important. See through the noise. Here's some more noise. This one is the left tweeter, and you can tell that spike is narrower around that time 0 point. And this looks really noisy. I don't think this was a car going by, Kevin. What happened here?
No, I think I sneezed on this one.
All right. So, look, the reality is, guys, you're probably not living next to a racetrack, and you're probably not capturing things while you're sneezing in the car. But you may be working in a noisy shop. You may be doing this in the driveway of your house, and a car may go by when you're looking at impulse response. Or someone may turn on the air compressor or the air conditioner, the high value, the HVAC kicks on and causes a noise, or a truck goes by. It's very easy to get noise in your impulse response, and being able to see through that is important. Now, this is a dynamic reading, meaning that this is actually something that we captured in real time and happened to hit that space bar at the right time to capture that trace so we can show it to you. But just know when you're looking at impulse response measurements, to be able to determine what's noise, what's pre-ringing, and what's the true rise of the impulse, if it's going up or if it's going down, and where that beginning actually is. Getting it as close as possible is a really good thing, but as there are initial delays, this is not important to be dead on because we're going to make changes later. See through the noise. That is our goal. Okay, continuing on. So the polarity check and impulse measurements are all done at the same time. We're setting the reference delay on the very first driver. So you measure the tweeter, and you set that as the reference delay. You go to the next tweeter. That's on the, in the US, that's on the other side of the car. So that's probably going to arrive later. So when you get to the second one, it's a new reference. So you set that as the reference, and then you go to the next channel, and then the next. You go all the way down the stack, as I call it. You go down the stack, and you check every single driver in the system. If you're setting the reference delay on anything that's arriving later to the right of the current 0, if it's arriving later, you set that as the new reference. Then you'll go back, and you'll check each channel again, and you'll set what's known as a delta delay. It's the difference between where the early arriving signal is and where the new 0 is. So what that looks like is something like this. So we have our 0 set as 7.17. Again, the number is almost irrelevant. And we'll see that in this case, by the way, that's a subwoofer, that white trace. I'll let you look at that real carefully just for a second. That white trace is the subwoofer. It does not look like an impulse response measurement. It looks like just a line across the screen. But as you look, you'll see it's starting to rise up. But it's rising up so slowly that the peak is way, way, way off to the right. Completely invisible. But it has been aligned. The tweeter, as you see here, is arriving early, and it's going straight up. So the polarity is already correct on this one, right? So if it's arriving early and we want to make it arrive at the same time, we can add delay. We add a delay in the same screen as our as our measurement. So we're adding it directly into the DSP. This is the same as the Tune tabs delay field. It's the same exact thing, but you don't have to change tabs. You put that delay value in there, it moves the impulse response to start at the same exact point as where the subwoofer started. The reference delay and the delta delay are now lining things up at the same time. That's what we're talking about.
When working with VXI or MVI, of course.
Yes, of course. But got to assume a little bit here, right? Excellent add there, Rob. Okay, so next, we'll go to the next driver. You can see here that the yellow one is there. That's a mid-range driver. The white one is there. That's a subwoofer. It doesn't even look like an impulse response. But this tweeter is arriving early. So what we're going to do is we're going to take the delay, and we're going to put that value in there. In this case, it's 0.9 milliseconds to offset that, to have all three of them now starting at the same point. That's the goal. That's what we're looking for. So we're going to change the scale on this a little bit so you can kind of see what's going on. You can see that the blue trace here has some pre-ringing to it, which is okay. We can tell that the impulse response is actually starting somewhere other than that. And we can see that that rise goes up at the same time that the rise is starting on the yellow trace. It's hard to see on the subwoofer, but if that was our reference delay, we know that the time 0 is the beginning of that impulse response. When we zoom in, we can actually see what we need when we need to by being able to zoom into the different parts of it using the controls and tune. That's golden. If you look at the upper right-hand corner, let me bother my guys. I don't know if you can see where my cursor is. You'll see that there's zoom controls, and the one that's currently highlighted in the upper right-hand corner there is controlling both X and Y axis. That means you can make a box around the measurement and zoom directly into that one particular area. It's a nice little tool.
You know what's really nice is being able to capture those traces and being able to zoom up and see where they lie and stuff like that, rather than relying on it being a live measurement all the time, right? So if you need to go in and make some minor adjustments, it's a lot easier to see that in the comparison with all of the other drivers and know that you need to make some adjustments in there. So capture your data is
always
very important,
capture.
Right?
Always capture. All right, so looking at this graph here, we have the yellow driver that's lined up at time 0. The red one is arriving late or early, guys. We're running late on time, so I'm going to tell you it's arriving early. So what we can do is we can shift it over, and what we've done here is we've gone too far. We've put too much delay on this one, and now it's arriving late. So that red one is happening after the beginning of the yellow one. So here it's arriving early. Here it's arriving late. So when we talk about arriving early and arriving late, that's what we're looking at. Okay. Here's when they are aligned. And again, we have a little bit of pre-ringing in there, but we can still tell when that impulse is starting to go up or starting to go down. In this case, they're both going up. They are aligned at this point, and that's the goal. That's the idea of step 5 and 6, polarity and initial delays. With that done, we move on to defining and matching to targets. This tends to be iterative, as I mentioned earlier, that you may have to go through a couple of these steps a few times to get them exactly where you want. And then you'll repeat that as you go down the stack for the different drivers in the system. So in a general sense, this is what you do. You're going to look at the measurement and you'll change the targets as needed. So if you think let's say your target has a high pass filter set at 5,000 hertz for your tweeter, but your tweeter is looking pretty good with that safety filter on. Safety filter, let's say it's at 1,500 hertz, but you still have nice solid response and the driver is capable of being crossed over lower. You might want to adjust your targets, both your mid-range and your tweeter, so that the sum stays the same, but you could shift those corner frequencies down to a lower frequency for the tweeter so that can play lower and maybe improve the overall performance of the system. Just be careful not to go too low, because that's when you start breaking tweeters. Know your equipment well enough to know what the limits would be. Don't cross it over at 400 just because it seems to be okay. Don't do it. Make sure you follow the recommendation of the manufacturer whenever possible. Okay. Do the same thing with mid-range and mid-bass drivers. A little less common to be making changes there, but you may have to. I've noticed that I make changes from mid-bass to subwoofer. Sometimes the mid-bass drivers, for whatever reason, aren't able to keep up with the subwoofer. I'm looking at you, Glenn. I know that you sell a lot of subwoofers, and if you only have a pair of 6.5s up on the front doors, it's going to be hard to get those things to line up. So you might want to change some of those filter frequencies to allow some of the energy to be where it needs to be. And we recommend EQing to a band-specific target, a tweeter to a tweeter channel, to a tweeter target, mid-range to a mid-range target, and so on. Very often people are doing a sum target, and it gets a little tricky to try to get a tweeter to line up to a sum target that's going all the entire bandwidth. So we recommend having a target generator like the one we have in Tune that allows you to sum together tweeter, mid-range, mid-bass, subwoofer, whatever the case may be, so that you have a sum target and band-specific targets that add up to that. And then using a general method, then you'd adjust the levels once you get them all EQ'd, and then you move on to the next step. But when it comes to Tune and Max, again, it's still going to be iterative, but a lot of this stuff is all done as a single step. You know, we're looking at the measurements, we're adjusting the levels based on where it shows up on the screen. We're going to EQ to target and adjust the level so that they're, lined up to the level of the target. And we're going to line up the measured data so that it matches the level of the target data. So we're setting levels, we're EQing to target, and setting our high and low pass filters all pretty much at the same time. So when we're done with steps 7 through 10, we are truly done with all of them. It's just a matter of going down that stack again. And when we're done, that's when we start looking at channel interactions. And now the normal way that this is done is we start looking at the way things sum together. Now remember the 3 dB rule. The 3 dB rule tells us that if we take one piston and we double the piston size or double your speakers, you should expect a 3 dB increase. If you're also doubling your power, you should expect another 3 dB increase. So when you're tuning a system, and let's say you've muted all your speakers except for the right mid-bass driver, and you have that level on the screen, if you unmute the other driver, the left mid-bass driver, you've doubled your piston and you've doubled your power. So when they're playing together, you should expect the frequency response to increase by 6 dB. That's in a perfect world. We don't live there. We live in an imperfect world. And Jeffrey mentioned it earlier. We're trying to correct for imperfections or inaccuracies in our measurement. And this is one of them. But we're looking at a frequency response to determine a time difference. If we've already done our level matching, and we've already done a match to EQ, EQ match to target, that means the frequency response and level have already been matched. They've already been corrected. So if the summation is anything less than perfect, we're dealing with a time-related issue. It's the only thing we haven't looked at. But we're looking at it in a frequency domain, and that can be helpful, but you're kind of in the dark. You don't know where the time issue may be. We don't know exactly what is causing it. Is it a delay issue? Is it do you need an all-pass filter? Is it a polarity issue? I know we've already looked at the polarity, but now we're looking at the actual measured data. Let the data be your guide. So what we would recommend is that we would actually look at the phase data, and that's what Tune and Max can really do well for us. So I wanted to show this graph here. On the top is an impulse response. You can tell it's a tweeter because it says it in the bottom right-hand corner. But if you look at the phase data on the bottom, if you see phase data that looks like that, that is a huge red flag that you forgot something. If you're looking at that phase data and saying, oh my God, I can't tell anything out of that phase data, it's because you did not set I circled the wrong part. You don't have a reference delay. That should be scooted over to where it says reference delay. That value, the reference delay, should be something other than 0 at this point. Remember, we set a new 0 by setting the reference delay. And when you don't have a reference delay, the phase data is meaningless. It has no point of reference. Time. Phase and time are one and the same, and time is relative. Phase is relative. If there is no point of relativity here, we cannot make heads or tails of the phase data. When you actually set a reference delay, again, I circled the wrong part, but when you zoom in on that, the reference delay allows us to now look at the phase data, and you look, it looks a lot better already. You can actually tell the phase wraps, and you can see the true phase response of, even in this case, a tweeter, which honestly at higher frequencies, it's not that it's not important, it's just less critical at higher frequencies than it is at lower frequencies. Without a reference delay, phase data is off the table. You can't use it. So looking at this data here, by now you should know what we're looking at. It also says it in the bottom right-hand corner. It's the phase response of the subwoofer in this system. And you can see the phase wrap, it's starting roughly in the middle of the screen, and we're going to call that the 0 degrees of phase. And it slopes down to the right, and then it kind of wraps back up, and then slopes down to the right a little bit steeper, and then up, and then down to the right a little bit steeper, and eventually it just stops. It's stopping because the tune and max measurement system has what's known as a blanking characteristic. And what that means is, as the level of the driver that you're measuring goes below a certain point, it means that the data at that point is probably not relative to your measurement. So as your subwoofer goes to higher frequencies, the phase data, we don't care about it because the sub is not playing higher frequencies. So we'll blank out that data. You see some of the little dots up there. It's just a little bit messy, but you can truly see what matters most to us. And in this case, it's pretty much everything from about 350 down lower. So yes, the sub can technically play that high and there's enough energy there to get a phase data, but we really care most about the interaction point with a high and low pass filter, the low pass for the subwoofer and the high pass for the mid bass, the way they overlap. So if we capture this blue trace as we've done here for the subwoofer, this is the phase data. If we then take the mid bass data and we overlay that or capture, or look at that live, we can see that right around 65 hertz or so, they're perfectly lined up. It's beautiful. That's roughly the high and low pass filter frequencies for this particular system. But as you go slightly higher in frequency, you'll notice that the white line for the mid bass is steeper than the blue line for the subwoofer. And the wraps don't line up as you go higher in frequency. These changes in the phase response are telling me that there's something not lined up in time. That will show up in the summation on the frequency response, but we are looking at the time domain, which is a far more accurate and better way of looking at time-based behavior. If you can measure time, look at time. If you can't, then all you can look at is the summation on the frequency response. This gives you pinpoint accuracy. I can tell you right now that about 125 hertz, these two drivers are out of phase, completely out of phase. The mid bass and subwoofer are no longer working together at that frequency, which means they will cancel each other out to some degree. That will show up, but here you can see exactly where and exactly why. We think that's a better way. All right, so next up is step 12. We're already at step 12. Listening is vital, guys. You got to listen to the system. Don't skip this step. It's far too important. Get done with your objective analysis, the phase traces, the impulse responses, the EQ to target, the levels. Get rid of all the number stuff, all the stuff you can actually quantify and measure and compare. Get that done so you can get in that vehicle and start listening to that system. The faster you can get to this point, the more time you can spend on this, and the better the system's going to perform. This is the fun part. You're going to make minor changes here, some level changes here and there, maybe a cut on the EQ, or maybe a little bit of boost if you need that. If you find yourself making huge, major changes, you probably missed something in your process. It's very likely that one of the steps in the previous 11 things that we've covered was probably not done or wasn't done completely to its the full extent. So if you start making major, huge changes to frequency and level, you've missed something. At this point, you shouldn't have to change anything in the time domain. It should already be aligned. That the phase data will not lie to you. It'll give you the accurate representation at that microphone, what that time data should be. So you shouldn't have to make those changes. All of this should be level and frequency only. And when you're done, that's what you want to recapture, your level and frequency response data. You're probably not going to do this. But at this point, trying to capture time-based measurements is probably not really smart. And the reason for that is when you put the microphones in the vehicle, you should try to align and figure out exactly where they were positioned so that you could kind of go back to that. But variations of where that center microphone is, they're inevitable. So the exact data for time is probably never going to be exactly the same. But the frequency and the level should be, since we're using spatial averaging, that sphere that we were talking about earlier, that data should be pretty consistent. As long as you don't like move them 15 or 20 inches in any direction, you'll probably be pretty good. Try to capture that data, compare it to your original target, and go from there. Well, that's the process. And I am right at time, I think. Yeah, pretty close.
Pretty close.
So I'm going to jump out of the keynote if I can, unless you need me to keep it.
I don't think so.
Okay, stop sharing. Now I can see what everybody was saying about me.
All right. So
what questions came up? What I miss?
Really, we only had one question that I can remember that we didn't address in chat or in the session. And it was from Sacktown Steve saying he couldn't type fast enough, but he didn't want to interrupt you. Is a cleaner tune achieved by tuning a modified target or a listener preferred target compared to increasing levels after tuning to the original unaltered curve? And he says, say I add some sizzle by increasing the tweeter levels after tuning. I'm thinking this isn't preferred because simply increasing tweeter levels will excessively boost frequencies at and on either saw it cut off. He really did write a long one.
I think you're referring to the crossover, right?
Yeah, probably
right,
crossover.
So Steve, let me try to address this. I think I understand what you're talking about. So if you have a target that you've used before, the tweeter level should be kind of where you want it. Now, of course, each vehicle is going to present differently. And I know in more cases than not, the high frequency, usually above 10K, is going to start rolling off or tapering off in almost all cases. I would not try to raise that up. Now, of course, when you're listening to it, you might find yourself saying, yeah, the tweeter's not enough. And that would be a level change in almost all cases. And I know Rob, Kevin, and I, for many years, we've been talking about when you're doing tuning, you should boost never and cut always, right? Cut, don't boost. We're going to come back on that a little bit. We're going to say that you should cut most of the time and use boost very, very cautiously. And it has a lot to do with what Steve is kind of referring to by pushing energy into a driver after you've accounted for everything. Mm-hmm. You do run the risk of possibly overdriving that driver. And that would be a concern. So if you start pushing 12, 15 dB, you're looking for a problem. But, a couple of dB here or there, 2 or 3 dB, yes, it's doubling the power. But at those higher frequencies, it's probably less of a concern. What I would encourage you not to do when you're looking at let the data be your guide, if you see your tweeter is rolling off, do not try to force it to do something it doesn't want to do naturally. That's where you run into problems. If you're lacking that sizzle or that higher frequency extension, it may be because of the installation or the system design. The tweeter maybe is not capable of playing that way for you, or the location in the vehicle maybe is not conducive for that to be perceived by your hearing the way you want it to. So that may be going back to steps 1 and 2, reconsidering maybe adding a couple of extra tweeters if you needed to, or maybe changing the tweeters to one that maybe can extend up higher.
So after all of that, what was cut off was, in a nutshell, is it better to tune to the curve to achieve a smoother blending of the mids?
Gotcha. Okay.
I didn't want to interrupt you because you were on a roll and it's all important data. But yeah, so, is it better to tune to the curve to have that, smoother response and then adjust as needed? I think it's where he was going.
I would, me personally, I would probably, if I find myself doing what you're saying on a regular basis, I would adjust my target so that way my mid-range and tweeter still align with one another, but I just have a little bit more level on the tweeter end of things.
Yes, I would do the same. That's definitely what I would do. So I guess in short, Steve, if your current target is not getting you the results when you get into the listening position, you alter your target so that it will be closer to that when you get into the listening position. That is what step 13 is for. So if you get into a car, so let me back up. So when you start off with a target curve, the goal is, I like the way this car sounds. I'm going to capture the way it presents in terms of frequency and level, and I'm going to use that as my target so that the next car I tune will hopefully sound like that. So if that's what the goal of a target is, and I think it is, if you don't have that reference, you're not sitting in a car that sounds good, you pick one that maybe somebody else thought sounded good, like the one we have, or, there's a Whitledge curve, and there's a, Andy Waymeyer's got a curve, and, there's a bunch of different target curves that are out there. Pick one that you trust, be it a JL Audio curve or a competitor curve, pick one. If you don't have one, listen to it once you've tuned to it. If you've tuned to that curve and you don't like it, step 13, capture what you do like, and you start building your own curve. That's what it's all about. So if you don't have a curve, use ours. If you have a curve, use yours. If you're not sure what a curve is, develop your own. It's all about making it sound the way you want, which is why listening is the most important part. Again, I said it earlier, and it's sort of tongue-in-cheek, but if your target is bad and you match to target, you've matched to bad, right? So make sure your target is something that you like. So when you match to it, it's something you like.
So good question in here. As Steve said, thank you for that. That's what perfect. That's what I thought. Sorry for the long-winded explanation. Not a problem. Jeffrey was asking, when we were looking earlier at the combined left and right mid-bass phase trace to the live subwoofer, we talked about being out of phase around 125 hertz. Jeffrey was wondering if we can give an example of how we might correct that. Do we correct it with time or signal delay? Do we use an all-pass filter? How would we improve that, essentially 180 degrees out of phase wrap at around 125 hertz we just discussed?
It's an excellent question, Jeffrey, and it's tricky to answer without some supporting graphics, which I sadly right now I don't have. We do plan on doing some more dynamic trainings on this once we have a trade show coming up that my cart that I've been standing in front of for the past couple of weeks is on its way to that trade show. So when that comes back, we'll do some live demonstrations of all of this. But let's talk about it real quickly. We're in the bonus time here, so if people need to tune out, I totally get it. I ask you not to, but you're going to do it anyway. Anyway, so the tools that we're looking at when we're looking at time-based measurements. Now, an equalizer, when you make changes on an equalizer, in most DSPs, that will create some type of phase shift. It's minor, but it will change the time domain a little bit. If you put a high pass or a low pass filter, that will also change your time domain. But that's both of those are changing your frequency response as well. By the time you're at step 11, I think is actually the number when we're looking at the optimization of drivers, you have already accounted for frequency and level. So you should only be looking at time. So we have to look at what tools we have in our DSP tool belt that only address time without changing level or frequency, because those have already been addressed. So those tools include Polarity, which would be a 180 degrees. We demonstrated that earlier with the subwoofer. It was a direct mirror image. Now, the example that we had showed a 180 degree phase shift at a specific frequency, but not all of them. A polarity adjustment is going to affect all of them equally. So every frequency will flip as a mirror image. We were only looking at a very narrow area where they were out of phase completely at 180 degrees. So there's got to be a different tool. Another tool that we can use to affect time or phase would be delay itself. So we said earlier that we set our initial delays using that new reference and then putting our delta delays and offsetting so that everything lines up with whatever that 0 point was. If for some reason they don't line up, by adding delay, my hands are going to attempt to kind of show what happens, but the downward wraps that you see coming from the upper left-hand corner to the bottom right-hand corner, the steepness of that, as you add more delay, they'll get steeper and steeper and closer together as you go higher in frequency. That's showing that things are arriving later and later and later, right, as you do all of that. So that's what you're looking at. When you add delay, you're getting the lines to be steeper and closer together. So when you look at the comparison, if one line is steeper and further away, you can add delay to the other channel and make it steeper and closer together. That's something to consider. The next tool that we have in our tool belt would be an all-pass filter. What an all-pass filter does is much like a high-pass or a low-pass filter that's changing the frequency response and only letting high frequencies or only letting low frequencies pass through. An all-pass filter, by the name, it allows all frequencies to pass through, but it still has a similar effect as a high or low-pass filter in terms of the frequency response. It's going to add an additional wrap. It's going to basically flip the polarity at 180 degrees at a specific frequency without changing the frequency domain. So it's only changing time over a very narrow window. So the example that we looked at earlier, I noticed two things about the phase traces. One wasn't as steep as the other, so we would need to add some delay to it. And two, we may need an all-pass filter to get an additional wrap that was there on one driver that wasn't there on the other. So it's sort of a long-winded answer, but I did want to go through that because we need to remember that the frequency and level has already been accounted for on this process. So we're only looking at time-based things. Don't be afraid to use any of the three tools we talked about: polarity, delay, and all-pass filters to try to get those traces to line up. And again, let the data be your guide. It's not easy at first, but once you start looking at it, it's the same thing as EQing a frequency response to a target. When you see the target and you see the measurement, you make the changes using your EQ because you already know how to use that tool. These are new tools, and we're not accustomed to seeing time. It's different for us. And again, if you want to be better, you got to try something different. This is something different, and it may be better. Of course, we think it is, but this is what we're trying to help with. We want to kind of get into this different aspect of looking at time, making it line up, and getting the three pillars to be perfectly aligned. Going back to what Jeffrey said originally, making sure any imperfections, anything that's out of whack is back in whack, right? And time is an important part of that. And so often overlooked because of the complexity previously that had been in place. TüNing Max is really intended to make that a lot easier. So.
And what's really nice is those adjustments that you're making are all real time. So you can watch your phase traces move as you're making these adjustments. And the first couple times you do it, you'll start to maybe see patterns and what your tools you're using and the effect that they have. And, you know, after you do it a bunch of times, then you're going to understand, hey, I'm looking at this, I see this, or I see this, and you kind of jump into a certain tool right on and head on. But that real time is...
I'm so glad you brought that up, Kevin. One thing I want to make sure that everybody understands, if you're a shop that has a Max and you're doing this for the first time, don't do it with the customer waiting.
Yes.
Okay, please. Because the process you need to learn, you know, what we're sharing with you, if you haven't done it before, we encourage you to learn is do it on your vehicle, play around with it, save your settings, and just go in and start messing around. The fact that it's real-time data, as you put on the all-pass filter, you'll see the phase wrap change immediately. And you can change the Q of that, change the frequency of that, and see what it actually does. See how the phase trace changes. If it's getting closer to what you want, keep going. If it's not, turn it off. It doesn't cost you anything except time. And if a customer is waiting for you, you don't have that time. Don't do it then. Do it when you have a chance to learn how these tools work so that when you look at that data is being your guide. When you look at that data, you know what tool to use. So I know some friends of ours are watching, and I'm going to pick on them a little bit, but like, you know, if Glenn is doing an installation and he sees that there's a nail that needs to be hammered, he could either grab the back end of a screwdriver or he could grab a hammer, right? He knows the right tool. You may not use the right tool, but you know the right tool. By knowing how these tools work, you know when a hammer makes sense and you know when a screwdriver makes sense. You know when a Dremel tool makes sense and you know when a CNC makes sense. That's why we have different tools. They do different things. And if you're not sure how a tool works, do that on your time. Learn that on your time so that when your customer is paying you for this work, you're doing it efficiently and properly for them. Now, if you're a hobbyist, like many of us are, and you have access to a Max box, well, you got some really good friends or you got some extra cash laying around. Either way is fine. You can learn this at any time that you'd like. And it's not that complicated. Again, real-time data makes it a lot easier to learn how these tools all work. So just bear that in mind. Something's new, something's different. If there's time crunches that is asking you to get done faster, I contend that our process will be very fast and very efficient once you know how to do it. Yeah. The first time, it's not going to be that fast. Second time, it'll be a lot faster. Third time, you're in the money round there. That's where things get really good. Is once
it's not just the time part; it's the overall results. As Adam, found out, one of our reps in the Midwest, says the difference between his first. I've never heard of ham-fisted before. His first Max tune, and once he had a little more practice on it, it was significant. And that
that's an excellent point. Yeah. So, and I'll tell you that, I'll speak on behalf of Kevin and Rob. When we first started doing a lot of this time-based measurements, it was like, oh my gosh, I don't understand this. This is going to take forever. But over the past few years, as we developed this with some really smart people guiding us along, we've learned a lot of the tips and tricks that we want to share with you. And we are working on a guided process for this exact procedure that we're talking about. That'll be a document that we'll be able to share at some point in the not too distant future. A couple of people may already have access to it as we kind of vet out the, any typos or mistakes I may have made in writing it. But once it's all vetted out, you'll have access to it. And again, take what you want from it. It's not the only way, but the process is methodical and detailed to allow us to get very repeatable and consistent results in a very short period of time. And I think we've done a really good job with that process and with the tools that we now offer.
So, Kevin, to go back to two things you were talking about, Steve, and Kevin also with like the live measurements really does make it easy to learn the behavior of the tools you're using. Yep. I remember, when we knew Max was coming, I think it had to be 2.5 years ago. I remember Steve, Kevin, and I sitting in Steve's office with REW learning impulse responses and learning phase and what tools and when to use them. And, it was a long process because you'd have to run a sweep and measure and then kind of guess like, okay, let's try this, run another sweep and compare. Well, that didn't work. Let's try this, run another sweep. And, it got to the point where it was like, I understood in theory what was happening, but the application, I was like, this is, it's too long for me to figure out. That's not how I learn. And I remember once I got my Max box and started playing around with my car and my desk speakers and sub in my office, okay, when I did this, I see the traces moving here. Let me not do that. Instead of having to run sweep after sweep, It's all real time. So it really helps you learn what delay is going to do, what an all pass filter is going to do. And, it's the real time for me is really cool. And also going back to what we were talking about, for our retail partners, you have to learn how to use this. And as Steve said, it shouldn't be while the customer's waiting. But I've already spoken to a couple of our dealers that used it to tune their sound rooms or their display boards. Or, obviously, if you have a demo car with DSP, get it in there and learn it on that. But, don't just think of it for the car. You can use these to make your boards dialed in to give proper sounding demos if you don't have a vehicle available. Help with, I've always opinion, if you're a retailer, a demo car is without a doubt the way to go. But if you don't have that, you have your sound room, right? But acoustically, it's not going to be like what a car's like. It's typically big and cavernous. There's rattles, probably all sorts of phase issues because of the size of the room and all of that. So get your Max in your sound room or on your display boards if you have a DSP setup in there and get that dialed in. Make that the optimal experience if you don't have a dialed in car to put the customer in. You can still do presets. Like if you have VXI, have them, your customer, instead of standing dead center, have them stand to the left like it would be in the car. So they're closer to one side of the speakers, and have a preset where it's just a raw system. This is kind of like what your car will be like if your car was big. Right. And then have it dialed in with delays and get the phase dialed in. So even though now they're off to the left, that sound stage is dead center on your source units. Right. And show them what DSP can do. We can still do that in our rooms, and Max is going to really expedite the process to get your demos really dialed in to help mimic what it can do in the car. Right.
Excellent points, all of it. I do caution that when you're tuning something for a room or a home audio system, the way the data presents itself will be different than it would in a car. And I've struggled here trying to do some measurements in our area over here. It's much better to just go out to the car and do some real measurements out there if you can. I did talk earlier a little bit about some automations, and I just want to touch on it real quick before we say goodnight. Within Dune 4, and when you have Max and VXI and MVI amplifiers, there are two main automations, or micro automations as they call them, that you should pay attention to. One is what's known as auto set EQ to target. And that's a micro automation that allows you, once you've shaped your response and adjusted the level down to your target and put your high and low pass filters on, whatever's appropriate, you have the ability to have it use the EQ for that channel to automatically let the computer try to match it to the target. And you'll be able to see that, and you'll be able to see if it was effective or not, and you can make changes to the EQ on the fly if you need to, visible and not etched in stone. The other micro automation comes in when you have the Max box connected. You could do that, by the way, without Max. You could do that with a single microphone, whatever one you may be using. But if you have Max, you unlock another micro automation, which is the ability to find the delay. And what that's all about is we call it our true delay finder. And when you're looking at an impulse response, it will attempt to find the beginning of that impulse response. And it'll do its best to see through any of that pre-ringing and be able to see through some of the noise that may be a part of your measurement. It may not always get it right, which is why we show complete visibility and nothing etched in stone. You have the ability to make changes to that micro automation at any point that you want. Reject it, redo it, whatever you want to do. Additionally, you have the ability to just insert that as your new reference just by clicking a button, so you don't have to type anything. And if you've already done that and you found your reference, you have the ability to insert what's known as the delta delay, the difference between the arriving early signal and the reference delay. That can be inserted automatically by finding the delay and inserting the delta. And again, if it's not correct, you have the ability to see that and adjust it as you need to. So when I talk about micro automations and automations in general, those are the things that we're talking about. You see it, but now that you've been able to see what a true impulse response could and should look like, you'll be able to make sense of that automation. So there is no man behind the curtain. There is no invisible things that are going on. There is complete and open visibility to every aspect of that. And we think that's really important. You should know what you're doing when you're tuning a system, and having visibility and the ability to make those changes. That's something we feel is really important. Excuse me.
In the hardware,
earlier on, I posted a link to the Help Center article on how to use the True Delay Finder, and I just also posted a link to the Tune 4 Max section of the Help Center, where you can find the articles on using AutoSet EQ to target, the True Delay Finder, creating targets, capturing traces, and a bunch of other features of Tune 4 and Max. And there's even more coming, so make sure you check those out to get even more detail into those two features Steve was talking about today.
Yeah, and the nice thing about the hardware when you're dealing with a Max box, and I just get excited when we talk about them. It is capturing a lot more data than you're just utilizing with your micro automations. So a lot of things that are automated out there are processes that are automated and are including hardware. They kind of coincide with one another, and they're only capturing enough data to complete that automation, where when you're dealing with a Mac system, it's not doing that. It is capturing all of the data for you and allowing you to see how that data presents itself, and allows you to make smart decisions, or you can let the computer make some smart decisions for you and guide you along through there. So keep that in mind. It's not just those micro automations. We're not just capturing that much data. We are capturing everything on there, which is extremely, extremely helpful.
Cool. Well, we didn't say it up front, but I think you all expected me to go long today. I apologize for that, but as Kevin was just expressing, we get very excited about this. This has been a significant effort on behalf of dozens and dozens of people here at JL Audio, and Kevin, Rob, and I have the privilege to share a lot of this stuff with all of you, and we appreciate you watching. Lots more coming. Trust me on that. There's a ton of training content that we've been developing over the past couple of years that we're going to be bringing out as we go forward. So we do appreciate you watching. We're looking forward to hearing from you. And until next time, I'm going to say goodnight and thanks for watching.
And if you're at K-Fest next Thursday in Dallas, make sure you join Kevin and I for our 2 sessions on Tune 4 and the Max measurement system. Woohoo! Got to get that subtle plug in.
Awesome. Thanks, guys. Take care.
Good night,
Good night, everybody.